Nuclear power is one of the most powerful tools that humanity possesses with regards to generating the energy we utilise in our daily lives. The question of if and how this scientific discovery should be harnessed is deeply complex, however. It all starts with a neutron, whizzing past at high speeds. When this neutron travels past a heavy nucleus, such as the uranium commonly used in nuclear reactors, it is captured, being added to the nucleus. This creates a compound nucleus, for example turning uranium-238 into uranium-239. This new nucleus may then decay into a different nuclide. For example, uranium-239 could emit an electron as a beta particle to become neptunium-239, or be rapidly followed by fission of the new nucleus. But this is all dependent on the velocity of the neutrons, with faster neutrons, or those with greater thermal energy, having greater ability to cause fission. Most of the reactors utilised for energy generation today are thermal reactors. Neutrons are said to have thermal energy when they have been slowed down to a similar kinetic energy of the surrounding atoms in their normal thermal motion. In order to slow the neutrons down to this speed, a moderator, in many cases water, must be used. Thermal fission can only occur in isotopes of uranium, plutonium, and some other elements with higher atomic numbers whose nuclei contain odd numbers of neutrons. The probability that fission will occur is determined by the area surrounding the target nucleus in which the incoming neutron must travel, and increases as the speed of the neutron decreases. A chain reaction begins in the reactor when an alpha particle or helium nucleus emitter, such as beryllium mixed with plutonium or radium, is inserted. The alpha particles cause the beryllium to release neutrons, converting it to carbon-12. When these neutrons are captured by a uranium nucleus, the total energy is distributed between the nucleons now present in the compound nucleus. This nucleus is relatively unstable as it has been forced to excite and is likely to split into two smaller nuclei. The creation of these fragment nuclei is followed by the emission of an average of 2.45 neutrons, which can then go on to cause the fission of further uranium nuclei. This creates a chain reaction in the reactor. To prevent an exponential increase in the rate of fission occurring in the reactor, control rods made out of neutron-absorbing materials such as silver and boron can be inserted into the reactor core to reduce the reaction rate or be withdrawn to increase it. This chain reaction releases a great deal of heat energy. In order to facilitate this energy generation, nuclear reactors are efficiently designed to allow the chain reaction to occur. In the reactor, uranium, which is highly abundant, is used. Plutonium and thorium can also be used. This nuclear fuel is processed into ceramic pellets and stacked into sealed metal tubes called fuel rods. Over 200 of these fuel rods form a fuel assembly, and a single reactor core consists of several hundred assemblies, determining the power level. In the US, all nuclear reactors are light water reactors, cooled and moderated by water. Of these, 65% are pressurized water reactors, which pump water into the reactor core at high pressures to prevent the water from boiling. This heated water is then piped through a steam generator where heat is exchanged and steam is formed. The other 35% are boiling water reactors, which heat the water to steam directly inside the vessel. The heat energy produced in the chain reaction is then used to heat water into steam, spinning a steam turbine and carrying out mechanical work. An electric generator then converts this mechanical work into electrical energy. This technology has several benefits. Nuclear energy is a source of reliable, carbon emission-free electricity. Nuclear power plants are able to run for 24 hours a day for many months on end and have an operating lifetime of between 20 and 40 years, with some being used for over 60 years. The fuel used in nuclear reactors is also incredibly rich in energy, with a single pellet of uranium containing as much energy as 1 ton of coal. Nuclear generators also produce very little waste when being operated, and this waste can be recycled for energy production or directly disposed of. Many countries have been using recycled fuel for decades to partially fuel their reactors. In an age where change is necessary to prevent the effects of climate change, nuclear energy could be a key part in transitioning to carbon-neutral electricity generation. Executive Director of the International Energy Agency, Faith Burrell, has stated that without an important contribution from nuclear power, the global energy transition will be that much harder. However, there are several risks associated with the use of nuclear technology. The waste produced in the reactor, such as uranium mill tailings, spent reactor fuel, and other wastes, are highly radioactive and must be contained and its disposal managed. The waste can remain radioactive and dangerous for thousands of years, and as such requires a great deal of regulation in its handling, transport, storage, and disposal. This radioactive waste decreases in radioactivity over time through a process of radioactive decay. Radioactive waste with a short half-life, such as uranium mill tailings, are commonly temporarily stored before disposal to reduce the radioactivity of the material. Large volumes of this waste contain the radioactive element radium, which decays to produce the radioactive gas radon. Because of this, the waste must be stored near the facility and covered with a sealing barrier of clay to prevent the radon from escaping, and covered by a layer of soil, rocks, or other materials to prevent erosion. Spent nuclear reactor fuel, which is highly radioactive, must be stored in special pools of water, which act as a radiation shield. The spent reactor fuel can also be stored in dry storage facilities, using special outdoor concrete or steel containers. The United States does not currently have a permanent disposal facility for high-level nuclear waste. Despite its benefits, the use of nuclear energy comes with some very large risks. An uncontrolled nuclear reaction could lead to mass devastation. Several nuclear disasters have occurred, most famously Fukushima in Japan and Chernobyl in Ukraine. The Fukushima disaster occurred on the 11th of March 2011 after an earthquake and tsunami hit the northeastern coast of Japan, cutting off external power to the reactors and disabling backup diesel generators. This prevented the cooling systems from functioning in the reactor, with battery power quickly becoming exhausted and causing overheating of the fuel in the reactor. Radiation was released from the damaged reactors, contaminating an expansive area surrounding the plant, and 500,000 residents were evacuated. The Chernobyl disaster is considered to be the world's worst nuclear disaster. Taking place on the 26th of April 1986, during a system test, a surge of power resulted in an explosion and fire in a section of the power plant. The explosion released a great deal of radioactive material, which contaminated the Western Soviet Union and areas of Europe. The disaster forced the relocation of 220,000 people from their homes, and 237 people suffered from acute radiation sickness, 31 of these dying in the first 3 months. It is also estimated that thousands more will die of cancer as a result of contamination. Environmental impacts have also been observed as a result of these disasters. This can even be seen in the daisies that grow near Fukushima, with the radiation acting as a mutagen, altering the DNA of many organisms, causing these plants to grow to be deformed. These disasters have rightfully caused the public to be fearful of nuclear energy. Despite containment vessels surrounding nuclear power plants designed to withstand extreme weather and earthquakes to prevent these disasters, it is still possible for accidents to occur. This brings us to the story of New Zealand. A defining moment in our history was the decision to go nuclear free, and in my opinion, I think this was the best option. Current legislation does not rule out nuclear power, however, only prohibiting nuclear waste and explosives. So it is up to us to decide. Thanks to hydropower generated by damming our rivers, geothermal power exploiting our high levels of geothermal activity, and wind, New Zealand generates 82% of its electricity from renewable sources. Although we should aim to make this number 100% in the near future, it is not unrealistic to suggest that this could be achieved without nuclear power. In considering the damage that nuclear accidents have caused in the past, I think it is safer to focus on our current renewable technologies.